Okay, so far what we have looked at is we started discussing from last lecture about informed search algorithms, if you remember. We said that informed search algorithms are mainly categorized as best first search because they try to obtain the best next node to uh, expand from the fringe list. Okay, for doing that, they organize the nodes in the fringe list as based on the priority value with respect to evaluation function. Generally, the evaluation function is defined in terms of some sort of a cost. Now, this cost can either be the path cost. If it is path cost, its definition it comes with the definition of the problem, and hence the algorithm doesn't remain a informed search algorithm, but it can be considered as an informed search algorithm maintaining the priority queue as a data structure where the priority criteria is the path cost. Okay, now what options does the best first search has for selecting fn value? The second option that it has, if I consider g of n is to be the base case, the second option that the algorithm has is h of n, which is referred to as a heuristic value. And as the name suggests, it's a heuristic. It's not something which is fixed. It is an estimation. Estimation of what? Estimation of cost you may require to incur in order to reach goal node from the current node using or following the cheapest path. So it is an estimation of the cost you need to incur to reach the goal node from the node for which we are finding out h of n value using the cheapest possible path. So there may be multiple paths to the goal node, and we are in search of the cheapest path to the goal node from that node onwards. So we are totally paying no heed to the cost that we incurred into reaching the particular node, but we only focus on the cost that we may incur in future if we follow from this node to the goal node using the cheapest path. And that version of the algorithm, the best first search algorithm, is referred to as a greedy best first search algorithm. Generally, when you use best first search algorithm, the problems for which you are using them requires or has bigger state space, and so keeping nodes open in the fringe list for a lot of time and keeping unnecessary nodes which are already explored and found not to be goal nodes in the open fringe list is not desirable. That actually creates a lot of issue with respect to the space utilization of the overall implementation. Hence, we use, instead of tree search, the graph search version of the search algorithm. And that graph search version requires you to define a data structure called as closed list. And this is exactly what the slides tells you. Like, so open is a ascending order list of priority queue of the nodes that have been generated and have had the heuristic function applied to them. So whenever I'm generating a node, I apply the heuristic function, because after that only I will understand what is h of n. And since the greedy version of the algorithm assigns evaluation function f of n equals h of n, so I will compute f of n value and I will arrange all the nodes in the ascending, that is increasing order of the fn as priority for the nodes in the queue. Okay, so that is exactly what they say. Now, their successors has not been initialized yet. तो जो भी नोड आपके ओपन लिस्ट में होगा, इसका मतलब है कि उसका गोल टेस्ट नहीं हुआ है. I have not tested it to be a goal node or not. Okay, and the other important thing is, since I have not tested it to be goal node or not, I haven't actually expanded those nodes to generate the child nodes or the next successors. That is what is written, that is what is maintained in the open list. So all the nodes which I have come across so far, to whom I have applied heuristic function, obtained its fn value, are organized in open list as a ascending sequence of priority based on f of n. Next thing you need to understand is, for these nodes, the successors are not generated and the goal test is not performed. Closed list में क्या होता है? In the closed list, we have a set of nodes that are already have been examined. Okay, previously they must have examined at some level. Okay, because they had the fn value least at that time in the fringe list. उनको हमने evaluate किया है. We have already found that they are not goal node, and maybe we have expanded it. Okay, so this set, the closed set, actually helps you to check if newly generated node was previously generated or not. तो ये सेट का यूज क्या होगा, अननेसेसरी नोड्स को ओपन लिस्ट में डाल के बार बार रखना आप अवॉइड करोगे. Now as we said earlier as well, there may be multiple paths going to the root node, so मेरे ट्री में एक नोड बार बार जनरेट हो सकता है. In the search tree, one node can reappear because it may be in the part of the tree which is following a different path to the goal node from initial state, and that's why same node can reappear but its parent may differ. उसका parent different हो सकता है. तो हर बार जब ऐसा कोई नोड आएगा जो आप ने पहले देख चुके हो, आप इतना ही चेक करोगे, is it heuristic value less than the previous, then you will actually update the heuristic value and the parent node in the closed list. You won't put it in open list, you will keep it in closed list because it's not goal node already known by you. So you are avoiding repetitive check for the same node in the goal test. So you are doing avoiding two things here. One is, for the same node I am not retesting it to be goal node unnecessarily. क्योंकि मैं अगर ओपन लिस्ट में उसको डालूंगा, even if the heuristic value is better compared to the earlier one, then ओपन लिस्ट में होने के कारण वो फिर से निकलेगा, बाहर आएगा ओपन लिस्ट से, and you will again need to do a goal test which you are trying to avoid. Okay, we'll just see these steps very briefly in this particular algorithms version. So we start with open list just containing the initial state as usual. Sorry, it's not highlighted. As usual, we'll just put initial state in my fringe list until goal is found or there is no solution left. We are doing these three steps, A, B, and C. We are picking up first node from the open list. We already say that the open list is now a priority queue, prioritized based on f of n. That's the assumption. That's why they don't say it in this particular expression of the algorithm. Next is, we generate the successor for the node. Okay, here they have missed one step where we do the goal test and know that the given node is not a goal node. They have missed it. You should put it over here in between. So there has to be this step, pick the first node out from the open list, test whether it is a goal node or not. Okay, so here the goal test happens. They have missed it. I need to actually add it. I'm not sure, the version over here is an edited version of the slides from the book, so I'm not sure whether I have altered it for the expression last year or maybe that is not there itself in the algorithm. They have missed it at all. Okay, so there has to be a goal test over here. If the node is not a goal node, then you do the B part, which is what you generate the successor nodes. Now, for each successor, before deciding whether to put it in open node or a closed list, we need to test whether it is not in closed list. If it is not in closed list, fine, you put the node in open list, no issues. If the node is in closed list, then you will do what? Then you will change the parent of the current node when you get the heuristic value better than the earlier one. So consider a scenario where you have some open list which has nodes A and node B, okay, and a closed list where there is a node C. Now every node, when I say that they are in open or closed list, so this is my open list and this is the closed list. So what it means is, currently we have these two nodes which are unexplored but part of the successors that are expanded, and C is the node which we surely know that it is not a goal node and it is been explored already. And maybe we can assume that C's parent node is probably the node D, which is there here. Okay, I'm assuming that there is one more node that we have already explored, which is node D, and C's parent node is D, and the value for heuristic function for this is 10, and for this is maybe 11. Okay, now what happens is, say A is the least priority with respect to heuristic value, so I remove A from open list, and say A has a child node C, a child node maybe, yes, B. Okay, so those two child nodes are there for A, suppose, and this C has a heuristic value 9. Okay, and this B has a heuristic value, say, 5. Now this B is already there, which was the child node for D, and its heuristic value is maybe 6, I should say. I'll just write it below, 6, I should say. Now for paths and all, you will find this ridiculous, because C say like a short length distance to the goal node, why it would change? That is what your conjuncture would be. So the problems which are with respect to paths, the heuristic values are fixed. There is no that much of issue in this case. But for the problems like the one where we had that 16 puzzle or 8 puzzle problem, where we are shuffling the space in order to generate states or the substates, there this may happen. Okay, there this may happen that I may be following a certain path and I revisit a state, but when I revisit a state, I might have done some changes in the order of other numbers, because of which now the goal comes nearer to me than it was earlier. Okay, so think of a scenario where, say, suppose you are playing a game, okay, and a strategy based game where you have not explored the map and you are searching for a particular goal. Okay, at that time when you have not explored the map, you might not have seen the racer car somewhere in the map, and because of that your goal currently you will feel from this state is possibly far away. But later on, after exploring the map, you might have not have changed the state of the game, but you have seen that there is a racer car. Now because of this added information, your game state is still same, but you now know, because you have a racer car, you can reach the goal node within, say, least amount of time, maybe. Okay, so this is what the scenario is that I'm trying to explain you. So I have two lists, one is open list, the other one is closed list. In the open list, two nodes are there, A and B. In the closed list, there are two nodes, C and D. As I remove A, I generate two subnodes, B and C. A happen to be not a goal node. Then what I will be doing, I will be putting A into the closed list, because now there is no use of A any further for me in this search algorithm. Obviously this has to be 5 or less than 5, they say, because B is 6 here. So this I'm putting it over here. Okay, this is just an example that I've thought of right now, so don't worry about the numbers as such. Now I have two nodes, B and C. So what this particular loop is doing, this for loop is checking for each successor. So first I'll check for B. Okay, there is one single node in open list, which is B, which is with path cost C, but now there is not path cost, sorry, heuristic function value 6, that is f of n is equal to 6 for B, and now for this new node f of n value comes out to be 5. Okay, maybe B is child of A and earlier B was maybe a child of D. That's why these changes are there. Maybe I'm not sure why they are like this, but that may be the reason because of which these changes happen. So what will happen is this new B would be sitting at the lead before this B. This is what it says. If the node is not in closed list, add it to open list and prioritize the open list. Your open list is a priority queue, so B will always go at the head. So now what I'm getting is I'm getting path from B to the goal node with heuristic value 6, another path to the goal node with heuristic value 5, this path being ahead of the other path. So please remember that although I am seeing that the state is same, the nodes are different. The one which was already there in open list, its parent was different. So a different action took me over there in that place. Okay, and now there is a different action. Okay, थोड़ा सोचना पड़ेगा to understand what is happening, and hopefully you are not getting confused. Okay. Now, once I've done and decided that B is not there in closed list, so I'm putting it in open list ahead of the earlier B because it has a least value of heuristic function. Then I'll choose this second one, which is C9. So C is already there in the closed list, identical to what I have. Now what I will do is I will only change the heuristic value if I have a better heuristic value. So heuristic value, if it is a cost, smaller value is always better, and many a times it's cost, so its smaller value is better. So I'll update this then with 9, and since I'm updating C, I should also update in the node data structure the parent node, because now the parent node is A. This time it is A. Earlier it might be something different. We are not sure about who was the parent at that time. So I'll be updating the parent. So this is what this step means, which is highlighted and which you need to understand, and is an important step while you are solving a problem using a graph search algorithm. So this is a graph search algorithm for you, which is very much like a tree search, but it tries to maintain two data structures, open and closed list, which the other one does not use. Okay, so that's another important thing to note. Now, as far as the properties of greedy search are concerned, greedy search obviously is good with respect to time and space complexity. It is comparable to the uninformed search strategies that we looked at, breadth first search as well as uniform cost search. O b raised to m is the time complexity and similar is the space complexity. And this time complexity may change based on how good heuristic you get. So some heuristics will give you solution early. For them, the time complexity is much more smaller. Okay, they will explore smaller section of the whole state space, because M, as you see, is nothing but the maximum depth of the state space. That is what we say. So this is the upper bound of the time complexity. A good heuristic will have a very good improvement in the time complexity. So it all depends on how good your heuristic is. Now, how this good is defined, we'll talk about it a bit later. Right now, we'll just say that a good heuristic can dramatically improve the time complexity for greedy best first search algorithm. But there is no guarantee of improvement in space complexity, because it has to keep all the nodes explored, unexplored in the memory. Even with the thing like maintaining a closed list, we need to add some what you can say additional steps to done, so that can actually work out correctly. So space में वो कोई improvement नहीं देता using closed list. It tries to reduce the number of steps you do otherwise. So time complexity वो जरूर थोड़ा reduce करेगा, but that is not that much. जितना अच्छा heuristic मुझे provide करेगा. Now, the other 2 points are very much important when it comes to the discussion of greedy best first search algorithm, and why you need to mix the heuristic value with the path cost. The reason behind that is the greedy search algorithm, many instances, is not complete, because the algorithm can get stuck in a loop. So the algorithm has the drawback of that, like a depth first search, which can also get into a particular loop, because I'm moving into a particular direction. तो जो problem depth first search का था, एक ही direction में आप search करते जाओगे, वैसा ही greedy search algorithm एक ही direction में, गलत direction में जाता रहेगा, आगे जाता रहेगा. That's the issue. And because of that single एक ही direction में probe करने का जो issue है, that can lead you to easily into traps of a loop. एक लूप के ट्रैप में इजीली आप बैठ जाते हो. सो दैट्स द प्रॉब्लम विथ greedy based first search. As far as getting the optimal solution is concerned, Greedy best first search might not give you an optimal solution. You'll say why? The reason behind that is you are working based on heuristic value purely, which is purely an estimate. Now, what you will incur actually when you will consume a step may be totally different. This is because since the estimate can be over or under estimates of the actual cost that you will incur when you do the action, and that's the reason they are saying that it's not an optimal algorithm. So two important drawbacks of greedy best first search: one, it is not complete because it can get into loops, because it has a similar kind of a makeup like a depth first search which tries to probe into one direction. Since the greedy search is driven by the heuristic value, it will also be going into a particular direction where the heuristic value is taking you with the least value. Okay. It's not optimal. The reason behind that is the heuristic value is an estimate, and you are purely relying while coming out the search strategy based on the heuristic value. Since it's an estimate, it can be overestimate or underestimate, and that may actually lead to incurring a different cost value altogether when you actually follow the steps. And that's why you may not get an optimal solution when you are using greedy best first search algorithm. Now, what is the remedy? The remedy is to go for A star algorithm. So this algorithm is read as A star. This name is read as A